Any questions on that? Okay, so this gets us to one of the two laws that we're going to use for circuit analysis, Kirchhoff's laws. The first Kirchhoff law comes from conservation of energy, and it says that the sum of all the potential differences encountered while moving around a loop or closed path is equal to 0. So let me show you what we mean by that. Let's say we have a battery, a source of EMF, which I'll label as Psi. And let's say we have a resistor here, and we will have, let's say, a capacitor here of capacitance C, and we will have maybe another resistor here. I'll label this second resistor R2 and the first resistor R1. Let's take nodes that separate each pair of components. So I usually like to begin at the negative terminal of the power supply. I will call this node A, the positive terminal, node B, the point between resistor 1 and the capacitor, I'll call C, and the point between the capacitor and resistor 2, I'll call D. Now, each one of these has a certain amount of potential difference across them, and we're going to learn what they are in turn. But Kirchhoff's law says when we go in a complete loop and add up all of the potential differences between successive pairs of points, those potential differences sum to 0. So for this loop, we have the potential difference, and let's just look at it in turn. We're going to go from A to B through the battery, from B to C through resistor 1, from C to D across the capacitor, and then from D back to A across resistor 2. We will just call this path 1. So going along path 1, we have the potential difference, and let's do this complete loop starting from A. So the potential difference from A to A is equal to the potential difference from A to B plus the potential difference from B to C plus the potential difference from C to D plus the potential difference from D back to A. So we've now gone in a complete loop, and Kirchhoff's law guarantees that the sum of those potential differences must be equal to 0. Now, in walking through this circuit, this would mean that the potential difference across the battery would have a potential difference of Psi EMF, and I'm going to explain some rules for that. The potential difference across the resistor, well, in order to know the potential difference across the resistor, we have to assume a direction for the current. So let's assume the direction of the current is counterclockwise. That's a good assumption for this single loop circuit, because for this single loop circuit, the positive terminal is high potential, the negative terminal is low potential. Positive charges move from high to low potential. So going from high to low potential means that the current will be going clockwise in this loop. When the current goes across resistor 1, that resistor is going to dissipate some energy. So I'll just do minus IR1. That's the potential difference across resistor 1. The potential difference across capacitor C, we'll just call it, well, remember Valley College is quaint, means that the potential difference is equal to the amount of charge over the capacitance. Let's say that this circuit is not fully charged. So that means we have current flowing through it until the capacitor is fully charged. So with that said, we would have current or charge over the capacitance. And I'll just put charge with the time dependency because as the current charges, the amount of charge will continue to increase on our capacitor plates. So that's the potential difference across the capacitor. Then the potential difference across resistor 2 is IR2, and this sums to 0. Notice how this gives us an equation. Kirchhoff's law gives us a relationship between the voltages of the components in a circuit. And these relationships will allow us to find important information, such as how much charge is on our capacitor or how much current is flowing through our circuit. So Kirchhoff's first loop law, the sum of all the potential differences encountered while moving around a closed loop is equal to 0. Excuse me.